Hello everyone, I'm Shashwat Kadam, and in this video we will take a look at the famous paper in distributed systems, Impossibility of Distributed Consensus with One Faulty Process. This paper was published by author Fischer, Lynch and Paterson. So let's get started. Let's start with the abstract of the paper. The consensus problem involves an asynchronous system of processes, some of which may be unreliable. The problem is for the reliable processes to agree on a binary value. In this paper, it is shown that every protocol for this problem has the possibility of non-termination, even with one faulty process. Let's break this down line by line. The first line says that the problem involves an asynchronous system of processes, and some of the process may be unreliable. The word unreliable means that not every process will be playing by the rules and may not produce desired results. In this case, it is assumed that unreliable process crashes. The remaining reliable processes try to agree on a binary value, 0 or 1. To agree on a value means that all the processors in the agreement situation will produce the same value when decision is to be taken. And lastly, if there is a faulty processor, every consensus protocol has this possibility of non-termination. Now let's take a look at what a consensus problem is. Getting the processes to agree upon one value is one of the most fundamental problems in distributed systems. Many applications require this, including conflict resolution, leader election, etc. Typically, a consensus problem is solved using a consensus protocol. And in a consensus protocol, we have a system of non-faulty and faulty processes. All the non-faulty processes eventually decide on value. That means a consensus protocol eventually terminates. All the processes that decide do so on the same value. That means there is a mutual agreement between the processes. The value that has been decided must have been proposed by some process. So the value which is the decision should not be generated from some random sources. It must be generated by one of the process. Let's get started with the actual FLP result. But before we delve into the proof of impossibility, we have to get familiar with the environment the processes are operating and different assumptions that are made to model our system. Let's start with the assumptions. The consensus problem is binary. That means the processes in the system can decide on either 0 or 1. We assume atomic broadcast. A process can send the same message to multiple processes in one step. It is assumed that if one non-faulty process receives the message, the other non-faulty processes will also get the message eventually. As we are in the asynchronous world, the messages can be delayed, arbitrarily long, and delivered out of order. Each process in the system behaves as automata. The process, depending on the message it receives and its current state, changes to a different state with the help of a transition function. The processes are fail-stop. That means the process will stop working if it fails. Let's take a look at our processes in the system. In our protocol, we have n processes, and naturally n is 2 and above, as consensus is needed when there are more than one process. Each process P has 3 attributes. The input register XP, which is 1-bit register and can only store 0 and 1. The output register YP, which informs us about the decision of the process at the end of the protocol. It can take 3 values, B, 0 and 1. The value B tells us that the decision is not yet made. And we also have unbounded internal storage for all the internal processing. Each process is deterministic. That means the transition function will not go to different states for same input. Normally, every process will start with some initial value XP and YP is equal to B when the decision is made. YP will have 0 and 1. YP is what write once register. That means after changing its value, we cannot change it again. So this diagram summarizes how a process looks. So we have an input register XP that can take 0 or 1, and output register YP which can take B, 0 and 1. Summarize what's going on in the protocol. We have all the processes on the left hand side with some initial value input register XP and YP equals to B. After applying the protocol, we see that YP has changed its value to 1 and processes have decided that 1 is their decision value. The states. We have defined our processes as automata, so the processes will transition through different states based on the transition function. The internal state of a process is the snapshot of process current state. It is the collection of the values in its input and output register, state of its internal storage, and its program counter. Every process begins with some initial value, initial state. The output register and the internal storage will have some fixed starting values. We know that output register starts with the value B. Input registers, on the other hand, can start with any value. The decision state is the state of the process where decision is made. That is, some value 0 or 1 has been written in the output register. The message buffer. Our system is modeled in such a way that the processes communicate with each other through a medium of the message buffer. The message buffer is a multiset, and it stores messages destined for processes. We have two function calls associated with the buffer. Send PM, a process calls this function to send message M to process P. The buffer will then put this message in it. Receive P is a function call which a process calls to retrieve a message from the buffer. It is a non-deterministic operation. It either returns the message and deletes its entry from the buffer, or it returns null and doesn't change the buffer. Now, why does it behave like that? We know that the processes in the system are deterministic, but the non-determinism associated with the asynchronous setting is simulated using this message buffer. So with the help of this message buffer, we can simulate the unbounded delays and other problems associated with the asynchronous world. Configuration is a global view of the processes and the message buffer at any particular moment. So in this case, we can see that there are different processes and their internal states are recorded, and at the same time we have this message buffer and its current state. So these together form the configuration of the system at that particular moment. Steps and events. If a process changes its state after receipt of a message, the configuration is changed. This change in configuration is called a step. Now, the configuration change that happens in a step depends on what process is accepting what message, that is, the tuple p, m. This message that triggers the configuration change is called an event. Different events lead to different output configuration. Here you can see that initially it was configuration C0, and after applying event E to it, it changes to configuration C1, which is one step. Schedules and runs. A sequence sigma of steps that is applied to a configuration to generate a new configuration is called a schedule. The sequence of the step itself is known as run of the schedule. Depending on what protocol it is, whether it has terminated or not, the run can have finite or infinite steps. Here we can see that after applying events, the configuration forms a list. So this list is called the schedule of the configuration. In this diagram, we can see that we start from an initial configuration C0, and after applying different events, we get different configurations C1, C2, C3, and so on. These different configurations will themselves apply different events and result in different configurations. In this case, we can see that it's CA and CB for C1. And so effectively, the configurations form a tree-like structure. Reachability and accessibility. Reachability. Any configuration C prime that can be achieved after applying a schedule sigma to the configuration C is reachable from C. In other words, we can say that there exists a path between C and C prime. In this diagram, we can see that configuration CB is reachable from C1 because there exists a path between them. Accessibility. A configuration is said to be accessible if it is reachable from some initial configuration. In this case, we can see that configuration CC is accessible from initial configuration C0 because there exists a path from root to that node. We have now arrived at our first lemma that says, if we have two disjoint schedules, they commute. In other words, if we apply two disjoint schedules in any order, we will end up on the same configuration. The schedules are said to be disjoint if the steps in them do not apply on any common process. Now in this diagram, consider we have initial configuration C0 and there are two schedules sigma and sigma prime which are disjoint. After applying sigma to C0 we get C1 and applying C prime to C0 we get C2. And then if we apply sigma prime to C1 we will end up having C3, and that will be the same as applying sigma to C2 because the steps in sigma and sigma prime are disjoint. Admissibility and decidability. A run is said to be admissible if it has at most one faulty process. That is, we allow one process to crash in an admissible run. So now let's formally define what a faulty and non-faulty process is. A process is faulty if it takes finite number of steps in the run. This is because it crashes and can't perform any more steps, so it has a short lifespan. A non-faulty process, on the other hand, can perform infinite steps because it continuously works based on the inputs it gets. A run is decidable if some process reaches deciding state. So we have a run and we have all these different configuration changes, and in one configuration one of the process reaches its deciding state, that is the output register has value other than B. So in that run we say that the run is decidable. Now that we are familiar with the environment and the different components of a consensus protocol, let's find out why it is impossible to achieve consensus in presence of a faulty process. There are a few more terms that will help us in our proof. Decision value is the value V decided by a configuration if the processes have decided on V in their decision states. Partial correctness. We know that for a totally correct consensus protocol, we need to satisfy the conditions of agreement, validity, and termination. A protocol is said to be partially correct if no accessible configuration has more than one decision value. That means we satisfy the agreement condition. And for each V belongs to 0 and 1, there is an accessible configuration with a decision value V. That means we satisfy the validity condition. The paper also defines a term totally correct in spite of one fault. A protocol is said to be totally correct in spite of one fault if it allows admissible runs, that means we allow one process to crash, satisfies the partial correctness of the protocol, and also terminates with a decision. We define the terms univalent and bivalent configuration based on what the configurations end up on. A configuration is said to be univalent if all the admissible runs from that configuration decide on a single value. So for example, if we have the configuration C0 and we evaluate all the possible runs, and if all the possible runs end up on decision 0, then we say that configuration C0 was univalent with value 0, or simply 0 valent. If a configuration C is univalent, then all the configurations reachable from that configuration will also be univalent. On the other hand, a configuration is said to be a bivalent configuration if some of the runs from that configuration end up with value 0 while others end up with value 1. So in a sense that a configuration is leading to an undecisive format. Suppose a B is a bivalent configuration, then its successor may either be 0 valent or 1 valent. We will try to prove the FLP result in following manner. We will first declare that our protocol is totally correct in spite of one fault. That means the protocol terminates with a valid decision value and it allows for one faulty processor. Then we will try to find out situations that contradict our assumption in following steps. First, we show that for any protocol there will be some initial configuration that is bivalent or indecisive. Then we will proceed to prove that there will be another bivalent configuration reachable from it, and then continue to show that a bivalent configuration will appear ahead again and again, leading to an infinitely indecisive run. And then we will conclude that if the run is indecisive and consensus will not be achieved. Let's get started with the proof. The authors proved two lemmas and used the result to prove the final result. Out of them, lemma 2 says that for a protocol P, there is an initial configuration that is bivalent. We will prove this by contradiction. So we will assume that P does not have any bivalent initial configurations. Therefore, it will only have initial configurations that are 0-valent or 1-valent. Now these initial configurations can be arranged in form of chain, where two neighboring configurations differ only in initial value xp for a single process P. For example, here you can see that configuration C0 and C1 have identical xp values for every process except for process P, where in C0 it has value 0 and in C1 it has value 1. The configuration C0 and C1 are therefore called adjacent configurations. As we know that every initial configuration is either 0-valent or 1-valent, there will be a case in which one of the two adjacent initial configurations will be 0-valent and the other will be 1-valent. In this following example, we can see that configuration C0 is 0-valent, which is adjacent to configuration C1, which is 1-valent. We are allowing admissible runs, so one process is allowed to fail. Assume process P fails and performs no steps in the run. Therefore, process P will not be responsible for any configuration changes. So we can neglect P from C0. Now the only difference between C0 and C1 has been neglected. Then C0 and C1 are in a sense identical. Now let sigma be the schedule applied to C0 to get a decision of 0. If we apply the same schedule to C1, then we will get the same result because the sequence of the steps and initial configurations are identical. Let's apply sigma to C1. We know that sigma will not contain any event associated with P. Therefore, P will not participate in configuration changes when sigma is applied to C1. Hence, P takes no steps in C1. Therefore, both C0 and C1 will take same steps. If both of them are taking same steps, both of them must end up on same decision. But one thing to notice here is that C1 was actually 1-valent from given condition, and applying applying the schedule sigma, it makes it 0-valent. Therefore, this contradicts our assumption that C0 and C1 decide on different values. So either one or both of C0 and C1 can potentially decide on 0 or 1. Thus, this contradicts our assumption that P only has univalent initial configurations because C1 or C0 are both potentially bivalent. Therefore, we have proved that protocol P has bivalent initial configuration. Now we have covered the first step of the proof. Let's move ahead and prove that there's a bivalent configuration reachable from a bivalent configuration. The authors elaborate on this in lemma 3 that says, let C be a bivalent configuration of P and event E be an event that is applicable to C. Let capital C be the set of configurations reachable from C without applying E, and capital D be the set of all the configurations after applying E to the configurations in capital C. Then set of configurations after applying E will contain a bivalent configuration. This can be summarized in the figure following. So we have a configuration C and we have all these different configurations which are obtained without applying E, and after applying E to each one of these we will get the corresponding configurations, and those corresponding configurations will lie inside D. We are trying to prove that if C is bivalent, then one or more of configurations in this set will also be a bivalent. First, let's assume that sigma is a schedule that does not contain E. Then E0 belongs to set capital C. After applying event E to E0, suppose we get F0. Then from the definition, we know that F0 belongs to set capital D. If E0 is 0-valent, F0 must also be a 0-valent because any configuration reachable from a univalent configuration is also univalent with the same value. If sigma is a schedule that does contain event E, then there is a configuration, say F0, on the path to E0 that is the result of applying E on its previous neighbor. In this case, it is C prime. F0 is a result of applying E, therefore it must belong to set D of configurations according to the definition. E0 is zero valent, and we know that F0 will be a zero valent configuration if it appeared after E0. But what if F0 is preceding in the schedule than E0? How can we prove F0 to be a zero valent? Because F0 belongs to capital D and it only has univalent configuration, and if F0 were one valent, then it cannot produce zero valent configuration in the run. Therefore, F0 has to be zero valent. We have shown that F0 is a zero valent configuration that resides in set D. Similarly, we can show for F1 using E1, which is a one valent configuration, that it also resides in set D. Therefore, set D contains both zero valent and one valent configuration. Next part of the proof deals with showing that one of the configurations in D is bivalent. We define a term neighbors. Two configurations are said to be neighbors if one is the result of applying a single event to the other. There exist two configurations E0 and E1 in set capital C such that E1 is the result of applying some arbitrary event E prime on E0. Therefore, E0 and E1 are neighbors. Let EI after the application of event E produce an I-valent configuration Fi. Two cases form based on the message E prime. Case 1. The processes P prime and P are not same. That is, the messages E prime and E are applying on two different processes. In this case, E prime and E are disjoint steps. Therefore, using lemma 1, we can figure out F1 is equal to E prime of F0. Here we can see that F0 is a zero valent configuration as per the definition, and F1 is a one valent configuration. And we are reaching a one valent configuration from a zero valent configuration. This implies that F0 must be bivalent for this to happen. This contradicts our assumption that set D only contains univalent configurations. Therefore, D contains a bivalent configuration. To complete the proof, we need to prove the result for another case as well. The case 2 is P prime is same as P. On the previous scenario with E0, E1, F0 and F1, consider a deciding run with schedule sigma for a process where a process P takes no steps. Let A be the resulting configuration. After applying the same schedule to F0 and F1, we say that B0 and B1 are generated. Since sigma is independent of P, schedule sigma and event E are disjoint. Then using lemma 1, we can establish following relationship. We know that P prime and P are same. Therefore, E prime and sigma are also disjoint. Therefore, we can establish the following relationship using lemma 1. Remember that A is a result of a deciding run. That means A cannot be bivalent. Now we know that F0 is zero valent and F1 is one valent. So therefore, B0 must be zero valent and B1 must be one valent. Let S be a mini schedule, E prime and E. Here we can see that E of A leads to a zero valent configuration and E of S of A leads to a one valent configuration. And we have already said that A is a part of a deciding run. That means A cannot be bivalent. But here we see a contradiction. Therefore, by contradiction, set capital D contains bivalent configuration. We have completed two steps in the proof. In first step, we showed that initial configuration of a protocol P has a bivalent configuration. Then we showed that from a bivalent configuration, it is possible to encounter another bivalent configuration down the run. Now if we combine these two results, suppose we start from a bivalent initial configuration, then using result 2, we will find a bivalent configuration down the run, and this will continue to happen again and again, and therefore this will never stop and our protocol will become indecisive. Therefore, if we have one multiprocessor, any consensus protocol has a possibility of non-termination. Therefore, we have proved that if a run is indecisive, consensus will not be achieved. Here are some of the references that helped me make this video. Thank you so much.